In July 2025, 3IATLAS looked ordinary. It wore the familiar signature of a comet, one clean jet of material streaming away from the sun, driven by heat, pressure, and nothing more mysterious than physics we've understood for decades. It behaved exactly as expected, predictable, reassuring. Then it went around the sun. When the Hubble Space Telescope looked again in December 2025, the object was no longer the same. Something had changed. The new images revealed a structure that immediately unsettled astronomers. There was still a jet pointing away from the sun, but now there was another one, fainter but unmistakable, and it pointed toward the sun. Two jets, opposing, balanced in a way that felt deliberate, almost conversational, like the object had turned around and answered itself. To understand why this matters, you have to understand how comets are supposed to work. Solar heat warms surface ice. That ice sublimates into gas. Radiation pressure pushes that gas and dust away from the sun. The process is simple. One direction, one flow. That's it. But 3IATLAS was now doing something else entirely. A sunward-facing jet doesn't just break expectations, it challenges the structure of the model itself. Heat shouldn't drive material inward, radiation pressure doesn't reverse, and yet, there it was, holding its shape across millions of kilometers of space. One explanation being considered is something called thermal lag. During its close pass around the sun, Atlas absorbed enormous amounts of heat, but that heat didn't vanish when it moved away. Instead, it may have slowly conducted through the object's interior. As the body rotated, regions that had been cold and shadowed, the comet's night side, began warming later, releasing gas with a delay. The result would look exactly like what Hubble saw: one jet driven by direct sunlight and a second jet powered by stored internal heat. It's a grounded explanation, rooted in known physics, but it requires Atlas to have an unusual internal structure, capable of holding and redistributing heat far more effectively than most comets. Another explanation is subtler: particle sorting. In this scenario, there may only be one true source jet, but solar radiation pressure doesn't affect all material equally. Heavier dust grains resist the solar wind and drift sunward. Lighter gas molecules and fine dust are pushed away more easily. Over vast distances, this separation can stretch a single jet into two distinct structures, one dense and narrow, one faint and diffuse, pointing in opposite directions. No exotic behavior required, just time, distance, and physics playing out on an enormous scale. Still, the geometry is persistent, stable, clean. And that's why even cautious scientists allow themselves to ask one more question, not as a claim, not as a conclusion, but as a thought experiment. What if the jets are functional? What if a sunward plasma stream acts as a radiation shield, while a rear jet stabilizes rotation or clears debris from the object's path? There is no evidence for this, none. But in science, even unlikely ideas serve a purpose. They define the boundaries of observation. They tell us what measurements would definitively rule them out. And that brings us to the real turning point. Speculation ends where data begins. The James Webb Space Telescope has the ability to resolve this mystery in a way Hubble cannot. Webb can analyze the chemistry of each jet independently. It can measure velocity profiles. It can detect subtle differences between gas and dust that reveal whether the jets share a common origin or were born separately. If their compositions differ, thermal lag gains strength. If their velocities diverge, particle sorting becomes likely. Webb doesn't guess, it decides. Meanwhile, astronomers are watching something else just as closely: the object's rotation. Before perihelion, 3IATLAS displayed a steady, repeating brightness cycle roughly every 16 hours. A heartbeat, a clock. If mass is now being lost unevenly, that rhythm could change. The object could spin up or slow down. Either outcome would reveal what lies beneath the surface, whether Atlas is solid fractured or barely holding together. The jets aren't just beautiful, they're diagnostic. They are fingerprints of structure, strength, and history, etched into space by an object that no longer behaves the way it used to. Whatever happened near the Sun didn't just heat 3IATLAS, it transformed it. And now, every new observation is no longer asking what it is, but what it became. As 3IATLAS continues its journey away from the Sun, one truth has become impossible to ignore. This object refuses to sit comfortably inside our definitions. It isn't breaking the rules of physics, but it is exposing the edges of them. The double jet doesn't signal failure in our models so much as incompleteness. And that, in many ways, is exactly what interstellar visitors are meant to do. They arrive carrying chemistry we didn't expect, structures we've never tested, behaviors shaped in environments our solar system has never known. 3IATLAS didn't form here. It wasn't sculpted by our sun. It brings with it the fingerprints of another stellar neighborhood, one we can't yet sample directly. And when such an object behaves strangely, the correct response isn't fear or fantasy, it's attention. As Atlas fades into the outer darkness, it leaves behind more than striking images from Hubble. It leaves uncertainty, productive uncertainty, the kind that forces better questions, sharper instruments, and humbler assumptions. Whether the double jet is driven by delayed heat, particle sorting, or a process we haven't yet imagined, one conclusion is already clear. The universe is more inventive than our models allow, and this will not be the last time we are reminded of that. More interstellar objects are coming, faster ones, stranger ones, and the next visitor may challenge us even more deeply than this one did. This story is not finished, it's still unfolding, and the moment the next piece of data arrives, everything we think we know may shift again.